Hey everyone, and welcome to This Explainer. Have you ever wondered what a chemical reaction actually looks like behind the scenes? Today, we're basically playing the role of microscopic detectives to uncover those hidden secrets. We always see chemistry written out as these neat, simple equations, but the reality at the atomic level? It's a bustling, complex, and completely invisible world. So let's figure out exactly how scientists track these invisible transformations.
Right, let's dive into the ultimate mystery here. We all know that A plus B equals C, but what exactly happens in the middle? How do we actually track invisible atoms as they transform during these wildly complex reactions? Knowing your starting ingredients and your final product is one thing, but mapping out the precise pathway the atoms take, that requires some incredibly clever techniques. It's essentially the chemical equivalent of wiretapping.
The very first tool in our detective kit is something called isotopic labeling. Think of an isotope kind of like an identical twin who's just slightly heavier. It has a variation in its neutron count, which means it behaves exactly the same in a chemical reaction. But that tiny bit of extra weight? That allows us to track its exact movements, like a microscopic GPS tracker, right through a biological cell or a metabolic pathway.
Section 1. Tagging the suspect with isotopic tracers. So we basically have two main categories of trackers to choose from. On one hand, we've got stable isotopes. These are completely safe, non-radioactive, mass-dependent labels, things like carbon-13 and deuterium. On the other hand, we have radioisotopes. Now, these act like tiny beacons that literally broadcast their location through radioactive decay, kind of like the fluorine-18 they use in hospital PET scans. Basically, the suspect we're tracking dictates the tracker we choose.
Section 2. Reading the clues by interrogating molecules.
Okay, so we've bugged the atom, but how do we actually listen in? Well, we need specialized magnifying glasses to read the clues. Nuclear magnetic resonance, or NMR, is basically a fingerprint scanner. It detects unique nuclear spins and hyperfine splitting signals. Mass spectrometry is like a highly precise scale, separating molecules by their literal weight to find differences in mass, isotopic fractions. And chronoamperometry, that's our high-speed camera, tracking time-resolved electrical currents to capture the fleeting, very initial stages of reaction.
So, how do we put all this together to map out, say, a living cell? It's a process called metabolic flux analysis. First, you feed the cell your isotopic label. Next, you just let the cell grow and reach a steady state. Then you analyze the output metabolites to determine the unique isotope pattern left behind. Finally, by calculating the magnitude of that flux, you've essentially drawn a real-time traffic map of the cell's metabolism, seeing exactly how fast and where the atoms traveled.
Section 3. Taking this from human bodies to oceans.
Now, because stable isotopes are completely radiation-free, they are incredibly safe. And this is an absolute game changer for human health. It allows researchers to track the absorption of essential minerals, like iron, zinc, and calcium, without any risks whatsoever. So it's the perfect, safe alternative to radioisotopes for pregnant or lactating women. By measuring trace element enrichment in blood plasma, urine, or breast milk, scientists can precisely assess our physiological and dietary requirements.
But, we don't have to stop at the microscopic scale of human cells. We can actually scale this exact same methodology up to the largest canvas imaginable, the Earth itself. We're talking about going from tracking zinc in a human body to tracing global currents across the entire planet. By using naturally occurring isotopes as microscopic clocks, oceanographers can solve mysteries across some staggering timelines. Take radium-223. It has a half-life of just 11 days. So that's perfect for tracking, it's perfect for tracking local bay and estuary circulation. But if you want to map global ocean circulation patterns, you'd look for lead isotopes, which track timelines of 50 to 200 years. And to uncover multi-million-year tectonic processes and climate changes, you'd look at rubidium-strontium ratios. It's just wild how scalable this is.
Section 4. Modern Frontiers and Automating Discovery. As you might guess, our detective work is getting a massive AI upgrade. We're now seeing the autonomous exploration of chemical reaction networks using computational algorithms, like Chematon 2.0. Instead of a human analyzing data for years, computers can predict and map out complex reactive molecular pathways on their own. It radically speeds up chemical discovery without needing constant human oversight.
And the physical tools are getting way smarter too. Mass spectrometer can now be used to monitor fleeting reaction intermediates to actually predict enantioselectivity. In plain English,
That means we can use these tools to predict the exact physical 3D shape and outcome of complex molecules as they're forming. Section 5. Solving the CO2 puzzle.
Let's apply all this advanced detective work to one of the most critical environmental puzzles of our time. Scientists are working desperately to turn harmful CO2 into usable chemical products through electrochemical CO2 reduction, or ECR. The goal is to valorize CO2 as a chemical feedstock, essentially storing renewable electricity right inside its chemical bonds. But to pull this off efficiently, we have to understand the exact reaction pathways. Much like drawing that traffic map of a cell, tracking the distribution of isotopes helps us here too. If we introduce a labeled isotope and watch the output, say 50% is unlabeled, while 25% goes down one labeled product pathway, and the remaining 25% goes down another, researchers can piece together the exact branching pathways of how crucial CO and C2 products are formed. But here's the catch, and it's a big one. Conventional steady-state measurements often completely miss the complex interplay of electrochemical reactions, chemical reactions, and mass transport. If we only look at the steady state, we're totally blind to the vital clues hidden in the immediate transient stages of the reaction.
To solve this, scientists turned to chronoamperometry to provide a time-resolved diagnostic tool. This high-speed magnifying glass reveals that the very first step isn't just one simple reaction. It's an initial electrochemical reaction instantly followed by a homogeneous chemical reaction. Wait even a second for the reaction to settle, and you completely miss this invisible handoff.
Tracking this rapid sequence step by step is exactly what reveals how intermediates, like formate, are created. These time-resolved signatures inform the dominant pathways for sequential electron and proton transfers. And honestly, understanding this split-second pathway is absolutely crucial to designing better, more efficient catalysts for CO2 reduction.
So from mapping the metabolism of a single cell to tracing global ocean currents over millions of years, to capturing the split-second charge transfer of a CO2 molecule, the ability to track the invisible has fundamentally transformed science. It leaves us with a pretty fascinating question to close on. Now that we have automated discovery and time-resolved tools to wiretap the very building blocks of nature, what invisible pathway will we map out next? Keep your curiosity focused on the atomic world, and thanks so much for joining me for this explainer.